Entanglement, Einstein's spooky action, unpacked. Picture this. You have a coin and your friend has another identical one. Now, imagine your friend zips off to the other side of the universe in a blink. You flip your coin, heads, and instantly, across cosmic distances, your friend's coin lands on tails. Guaranteed every single time. Sounds like science fiction, doesn't it? Pure fantasy? Well, believe it or not, this little story, with a few tweaks, gives you a peek into one of the weirdest, most baffling things in the entire universe. Quantum entanglement. This is the very idea that got Albert Einstein so worked up, he called it spookhafte Fernwirkung, spooky action at a distance. And today, we're diving into that spookiness. What on earth is quantum entanglement? So, what is this quantum entanglement that had Einstein himself puzzled? Well, strip away the jargon, and entanglement is basically a super strong link between two or more quantum particles. Imagine particle A and particle B meet and interact. From that point on, they're connected. Their destinies are tied together, no matter how far apart they fly. The really wild part? You can't describe particle A on its own anymore, or particle B for that matter. It's like they've become one entity. Even if particle A is chilling in your lab, and particle B is vacationing in another galaxy. To know something about A, you have to know something about B, and the other way around. They share secrets, a kind of joint identity that distance just can't break. This isn't some magic trick. It's a basic rule of quantum mechanics, the physics of the super tiny. We're talking about a world where particles can be in many places at once, where just looking at something changes it. And these spooky connections? They're real, proven in labs over and over. Scientists are even finding entanglement between the heaviest known particles, top quarks, which is opening up brand new research areas. And get this spooky action has even been seen inside single protons, across tiny, tiny distances, just a quadrillionth of a meter. How does this spooky action actually work? Alright, so how does this spooky action actually play out? First, we need to talk about another quantum superstar, superposition. Think of a quantum particle, an electron, a photon, whatever, before you measure it. It doesn't have a fixed property like spin up or spin down or horizontal or vertical, nope. It's kind of all of them at once. It's in a superposition of all possible states. Remember our coin? It's like that coin spinning in the air. It's neither heads nor tails until it actually lands. So, when two particles get entangled, their superpositions get linked up. Let's say we entangle two photons so we know their polarizations will always be opposites. If you measure photon A and bam, it's horizontally polarized. Then photon B, wherever it is in the universe, instantly becomes vertically polarized. Right before you measured, both were in that fuzzy superposition state of being both horizontal and vertical. The moment you measure one, it's forced to pick a side, and because it's linked to its partner, the other photon instantly picks the matching state. Scientists call this the collapse of the wave function. One particle's measurement immediately affects the other, no matter how much space is between them. This instant connection is the spooky action that really bugged Einstein. It looked like information was zipping across space faster than light, which, according to his own special theory of relativity, is a huge no-no in physics. If you measure a particle here and it instantly changes a particle light years away, isn't that faster than light communication? That was Einstein's big worry. It kicked off decades of arguments and experiments. He even cooked up a famous thought experiment in 1935 with Podolsky and Rosen, the EPR paradox, to argue that quantum mechanics wasn't telling the whole story. They thought there must be some hidden variables, some secret information, setting the outcomes from the start. Bell's theorem, putting spookiness to the test. So, for ages, scientists debated, were these connections genuinely spooky, or was it all just preset information, those hidden variables Einstein talked about? It was a massive debate. Then, in the 1960s, along came a physicist named John Stuart Bell. Bell cooked up this really clever mathematical test, now called Bell's theorem or Bell's inequalities. Basically, Bell said, if the universe plays by local realism rules, meaning particles have their properties set beforehand, and nothing travels faster than light, then the connections between entangled particles can only be so strong. There's a limit. But if quantum mechanics is right, those connections would be stronger than Bell's limit. Bell's theorem gave scientists a way to actually test quantum mechanics against Einstein's more traditional view. And test it they did. Starting with John Clauser and Stuart Friedman in 1972, then Alan Aspect in 1982, and many others since, including Anton Zeilinger. In fact, Clauser, Aspect, and Zeilinger won the Nobel Prize in Physics in 2022 for their groundbreaking work with entangled photons. Again and again, the experiment smashed through Bell's limit, backing up quantum mechanics every time. The verdict was in, entanglement is definitely real, and those connections are far weirder than old-school physics ever imagined. There are no secret hidden variables calling the shots beforehand. The universe, deep down at its quantum core, is non-local. Things are connected in this spooky way. Faster than light communication? Not so fast. Okay, so if measuring one particle instantly affects its twin light years away, can we use this to send messages faster than light? Break that cosmic speed limit? The answer, and this might surprise you, is no. The connection is instant, sure, but you can't use it to send actual, usable information faster than light. Here's the catch. Think about those entangled coins again. You flip yours, it's heads. You know, right away, your friend's coin is tails. But here's the thing. Your friend has no idea their coin is tails until they look at it, or until you tell them, say, by calling them on the phone, which of course is limited by the speed of light. You can't make your coin land on heads to send a 1 or tails to send a 0. The outcome of your measurement is totally random. You instantly know what your friend's particle is doing once you measure yours, but you can't control your outcome to deliberately send a message. Your string of random heads and tails will look just as random to your friend looking at their coins, until you guys get together and compare notes. That's when the amazing correlation shows up. So, Einstein's theory of relativity is safe. Entanglement gives us this mind-blowing instant connection, but not instant communication of new info. It's a fine point, but a really important one. From spooky curiosity to revolutionary technology. So, this spooky action, once just a mind-bending puzzle for physicists, is now powering actual technologies that are set to change our world. Seriously. The United Nations has even named 2025 the International Year of Quantum Science and Technology. That's how big a deal this is. First up, the one you've probably heard about: quantum computing. Regular computers use bits, either a 0 or a 1. Quantum computers, they use qubits. And thanks to superposition, a qubit can be a 0, a 1, or both at the same time. Entangle these qubits, and their computing power explodes. We're talking about machines that could solve problems, like cracking today's toughest codes or designing brand new medicines, way faster than any supercomputer we have now could even imagine. big names like IBM, Google, and Quantinuum are already building processors with hundreds, even over 1,000 qubits, and they're aiming for even more powerful, reliable machines. We're already seeing early uses in drug discovery, fighting climate change, and making financial markets smarter. The quantum computing market. It's set to be huge, possibly worth tens of billions by 2035. Next, there's quantum cryptography, especially something called quantum key distribution, QKD. Using entanglement, we can create encryption keys that are, in theory, completely uncrackable. If a spy tries to listen in on a key being sent with entangled particles, just the act of them peeking disturbs the entanglement, and boom, everyone knows there's an intruder. China's Mischius satellite, for instance, has already sent entangled keys over thousands of kilometers, proving this could work for super-secure global communication. As current encryption methods start to look shaky against future quantum computers, these quantum-safe methods are becoming super important. And then there's quantum teleportation. Now, hold on, this isn't the beam me up, Scotty kind of teleportation. We're not zapping actual stuff from one place to another. Instead, quantum teleportation lets us transfer the exact quantum state of a particle, all its information, to another particle far away, without the original particle physically moving. The original state is sort of read and destroyed, then perfectly recreated in a distant, entangled partner. This is super important for building quantum networks. Think of it as a quantum internet. This network could send quantum information securely between quantum computers or supersensitive sensors. Scientists are making breakthroughs all the time, like recently entangling molecules very stably using tiny optical tweezers, and even using AI to help create entanglement more easily. They're also discovering new ways entanglement can happen, like with the spin of light in tiny nanosystems, which could lead to smaller quantum gadgets. These networks could totally change secure communications, how quantum computers work together, and make quantum sensors even more precise. Join the quantum conversation. Look, there's no doubt about it. Quantum entanglement is seriously weird, but in the best way possible. It makes you question everything you thought you knew about how the world works. So, what part of entanglement do you find the spookiest or most amazing? And which of these future quantum gadgets are you most pumped to see? Drop a comment below. We really want to hear what you think. And hey, if you want to explore more of the mind-bending world of quantum mechanics with us, definitely hit that subscribe button and ring the notification bell. You won't want to miss what we're diving into next. Embracing the spookiness. So, from Einstein scratching his head over spooky action at a distance, to becoming the engine for mind-blowing new tech, quantum entanglement has come a long, long way. It went from being a puzzle that baffled the brightest minds to a tool that's changing the game. No, it won't let us send messages faster than light. But those instant connections, that deep sense of everything being linked, that's not just reshaping how we see the universe. It's reshaping what we can do. The quantum age isn't on the horizon. It's here, and entanglement is right at the heart of it. The spooky is turning into the spectacular, and the future it's building, it's going to be wild.